Hello there, and welcome to the Deep Somna. I'm so glad you found your way here tonight. Wherever you are in the world, whatever thoughts are circling through your mind, you can let them settle now. Let the day's noise soften. Let your breathing find its own gentle rhythm. Tonight, we're going to drift together through the vastness of space, exploring some of the universe's quietest wonders, the mysteries that astronomers and physicists whisper about in hushed tones, the questions that have no loud answers, only patient observation and careful thought. You don't need to remember everything you hear. You don't need to solve anything or understand it all completely. This isn't a test. This is simply an invitation to let your mind wander among the stars, to feel the gentle pull of curiosity without the weight of urgency, to rest in the presence of something vast and ancient and ongoing, something that was here long before you and will continue long after, something that holds you now in this quiet moment. The universe is unimaginably large. You've heard this before, of course. But let yourself feel it now, softly, without strain. Above you, even if you can't see it through your ceiling, through the clouds, through the city lights, the night sky stretches in every direction, hundreds of billions of galaxies, each containing hundreds of billions of stars, scattered across distances so immense that light itself, traveling at 186,000 miles every single second, takes billions of years to cross from one edge of the observable universe to another. And yet, for all these stars and galaxies, most of the universe isn't made of things we can see. Most of it is invisible. Most of it is unknown. And that's where our journey begins tonight, in the gentle mystery of what fills the cosmos, what holds it together, what pushes it apart, and why we find ourselves here at all. Brief sparks of awareness in an ocean of space and time. Let's start with something simple and visible. Let's start with a galaxy. Picture the Milky Way, our home galaxy. A great spiral of stars and gas and dust, turning slowly in the darkness. If you could step outside it, far outside, and look back, you would see a disk of light, spiral arms curving outward from a bright central bulge, the whole structure rotating like a cosmic pinwheel. Our sun is just one star among those hundreds of billions, located about 2/3 of the way out from the center, orbiting the galactic heart once every 250 million years or so. Now here's something curious. When astronomers measure how fast stars are moving in galaxies like ours, they find something unexpected. Stars near the edges of galaxies are moving much faster than they should be. According to the visible matter, the stars and gas we can see, those outer stars should be moving more slowly. They should be lazily drifting along, held only loosely by the galaxy's gravity. Instead, they're whipping around at high speeds, as if something unseen is holding them in place, something with mass, something with gravity, something we can't detect with our telescopes. This invisible something is everywhere. It's woven through our galaxy and every other galaxy. It forms vast structures, cosmic webs stretching across hundreds of millions of light years, connecting galaxy clusters like threads in an incomprehensibly large tapestry. Astronomers call it dark matter, though that name is more of a placeholder than an explanation. It doesn't emit light. It doesn't absorb light. It doesn't interact with light at all as far as we can tell. It's matter, because it has mass and gravity. But it's dark, utterly dark, invisible to every telescope we've ever built. And it's not rare. Dark matter makes up about 85% of all the matter in the universe. Everything you can see, every star, every galaxy, every nebula glowing in deep space photographs, all of it combined is only about 15% of the matter that exists. We are the minority. We are the strange exception. The universe is mostly made of something we cannot see, cannot touch, cannot directly detect except through its gravitational pull. You can let that sink in gently, without alarm. It's not a frightening thought. It's a humbling one. A reminder that reality is larger and stranger than what our eyes alone can show us. It's a little bit like being a fish in the ocean who has just discovered that most of the world is air, invisible and intangible from beneath the waves, yet undeniably real. Scientists first began to suspect dark matter's existence in the 1930s. A Swiss astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster, watching how individual galaxies moved within it. He calculated their speeds and realized they were moving too fast. The cluster should have flown apart long ago. There wasn't enough visible mass to hold it together. Zwicky proposed that some unseen mass must be present, something he called dark matter. Though at the time few people took the idea seriously, decades later, in the 1970s, an American astronomer named Vera Rubin studied the rotation curves of spiral galaxies, measuring how fast stars orbit at different distances from the galactic center. Again and again, she found the same pattern. Stars far from the center were moving too fast. The visible matter wasn't enough. Something invisible had to be there, spread throughout each galaxy in a great halo, holding everything together with its gravity. Since then, evidence has piled up quietly, steadily, like snow accumulating on a still winter night. Astronomers have observed gravitational lensing, the bending of light around massive objects, and found that the bending is stronger than the visible matter alone can explain. They've studied the cosmic microwave background, the faint afterglow of the Big Bang, and seen subtle patterns in its temperature fluctuations that match what we'd expect if dark matter shaped the early universe's structure. They've watched colliding galaxy clusters and seen the visible matter slow down from friction, while something invisible, something that doesn't interact that way, passes right through. All of this points to the same conclusion. Dark matter is real. It's out there. It's everywhere, in fact. Passing through this room right now, through your body, through the earth, utterly indifferent to ordinary matter. We are immersed in it the way a sponge is immersed in water, except we cannot feel it, cannot sense it directly, except through the way it shapes the motions of stars and galaxies across cosmic distances. But what is it made of? That's the question physicists have been asking for decades. And the honest answer is, we don't know. We have ideas, good ideas, ideas worth testing, but no definitive answer yet. Dark matter might be made of particles, exotic particles, that don't exist in the standard model of particle physics, the framework that describes all the ordinary matter we know. These hypothetical particles have names like WIMPs, weakly interacting massive particles, or actions, or sterile neutrinos. Each one is a possibility, a candidate, something that might exist, and might have the right properties to be dark matter. WIMPs, for instance, would be heavy particles, perhaps tens or hundreds of times more massive than a proton, and they would interact only very weakly with ordinary matter, mostly through gravity and possibly through the weak nuclear force. If WIMPs exist, they should be all around us. Countless trillions of them streaming through the Earth every second, almost always passing through without a trace. But very, very rarely, one might collide with an atomic nucleus. And if we build a sensitive enough detector, we might catch that collision, see the tiny flash of energy, or the faint recoil of the nucleus. Scientists have built such detectors. They've placed them deep underground, beneath mountains, or in old mines, shielded from cosmic rays and other interference. They've cooled them to temperatures near absolute zero and waited patiently for years, watching for the telltale sign of a dark matter particle. So far, most of these experiments have found nothing. The detectors sit in silence, but that silence, too, is information. It tells us what dark matter probably isn't. It narrows the possibilities. It teaches us patience and humility. Axions, another candidate, would be much lighter, far lighter than electrons, and they would interact even more weakly than WIMPs, primarily through their potential coupling to electromagnetic fields. Detecting actions requires different experiments, different strategies, often involving strong magnetic fields and highly sensitive equipment designed to catch the faint conversion of actions into photons. These experiments, too, run quietly in laboratories around the world, searching for whispers in the dark. And there are more exotic possibilities. Perhaps dark matter isn't made of particles at all, not in the way we usually think of particles. Perhaps it's something stranger, primordial black holes formed in the early universe, or some unknown field permeating space, or even a sign that our theory of gravity needs to be modified on galactic scales. This last idea, called modified gravity or MOND, tries to explain the same observations without invoking invisible matter, suggesting instead that gravity behaves differently than we expect when it's very weak across the vast distances between stars. Most physicists favor the dark matter explanation over modified gravity, because dark matter fits more of the observations more naturally. But science isn't about popularity. It's about evidence, and so the search continues, quiet and methodical, using telescopes and particle detectors and gravitational wave observatories, all working together to tighten the circle around the truth. You don't need to hold on to all these details. You can let the names and numbers drift away. What matters, what's worth carrying with you into sleep, is the feeling of it, the sense that the universe is far more intricate than it appears, that most of what exists is hidden, and that human beings, in our curiosity and patience, are slowly learning to read the invisible. Now let's zoom out further, beyond galaxies, beyond clusters of galaxies, to the universe as a whole, expanding in all directions, growing larger with every passing moment. This expansion is not like an explosion, not like fragments flying outward from a central point. It's more subtle than that. Space itself is stretching. The distances between galaxies are increasing because the fabric of space is gently unfolding, carrying galaxies along with it. Imagine dots on the surface of a balloon. As the balloon inflates, the dots move apart, not because they're sliding across the surface, but because the surface itself is expanding. That's a rough analogy for cosmic expansion. Every galaxy, every cluster, Every point in space is moving away from every other point. Not through space, but with space. For most of the 20th century, astronomers assumed this expansion was slowing down. After all, gravity pulls things together. It should act like a brake on the expansion, gradually slowing it, perhaps even eventually reversing it, pulling everything back together in a big crunch. That seemed reasonable. That seemed like how the universe should behave. But in the late 1990s, two independent teams of astronomers made a startling discovery. They were studying distant supernovae, exploding stars that serve as cosmic distance markers, and they found something unexpected. The universe's expansion isn't slowing down, it's speeding up. Galaxies farther away are accelerating, moving apart faster and faster as time goes on. This was shocking. It was like throwing a ball into the air and watching it accelerate upward instead of falling back down. Something must be pushing. Something must be counteracting gravity, driving the expansion faster. But what? Physicists call it dark energy. And like dark matter, the name is more of an acknowledgement of ignorance than an explanation. Dark energy is even more mysterious than dark matter. It makes up about 70% of the total energy content of the universe, far more than matter of any kind, visible or dark. It's everywhere, filling all of space uniformly, exerting a kind of negative pressure, a gentle repulsive force that pushes space to expand faster. No one knows what dark energy is. It might be a property of space itself, a cosmological constant, the energy of empty space, sometimes called vacuum energy. According to quantum field theory, even empty space isn't truly empty. It's a seething foam of virtual particles popping in and out of existence, and this activity might carry energy. If that energy has the right properties, it could act as dark energy, driving cosmic acceleration. But there's a problem. When physicists calculate how much vacuum energy there should be based on quantum field theory, they get an answer that's wildly, absurdly wrong, off by a factor of 10 to the power of 120 or so, one of the worst predictions in the history of science. Either the calculation is missing something fundamental, or dark energy is something else entirely. Another possibility is that dark energy isn't constant. Maybe it's a field, something called quintessence, that changes over time, growing stronger or weaker as the universe evolves. Or maybe it's a sign that general relativity, Einstein's theory of gravity, breaks down on the largest cosmic scales, and we need a new theory to describe how space and time behave across billions of light years. The truth is, we don't know. We have this enormous piece of the cosmic puzzle, 70% of everything, and we don't know what it is. We see its effects, we measure its influence, but its nature remains hidden, and that's okay. That's where science lives, in the space between what we know and what we don't, in the careful, patient effort to ask better questions and design better experiments. You can rest in that uncertainty. You can let it be okay that the universe holds secrets, that reality is not yet fully mapped. There's something that takes the pressure off, knowing that even the smartest scientists on Earth are still searching, still wondering, still waiting for the next clue. Let's bring our attention now to the very beginning, to the origin of it all. The Big Bang wasn't an explosion in space. It was the beginning of space itself and time itself, the moment when everything we know came into existence. Before the Big Bang, there was no before. There was no space to expand into, no time to pass through. There was simply nothing. Or perhaps something so different from what we call reality that our language breaks down. About 13.8 billion years ago, the universe began. It was unimaginably hot and dense, and it started expanding, cooling as it grew. In the first fractions of a second, the fundamental forces of nature separated from one another. Gravity split off first, then the strong nuclear force, then the electromagnetic and weak forces. Particles formed, quarks and leptons, the building blocks of matter. For a brief moment, matter and antimatter existed in nearly equal amounts. But for reasons we still don't fully understand, there was a tiny imbalance, about one extra matter particle for every billion matter-antimatter pairs. Those pairs annihilated each other, and the leftover matter, that 1 in a billion excess, became everything we see today. This asymmetry, this slight tipping of the scales in favor of matter, is called baryogenesis, and it's one of the deepest mysteries in physics. If matter and antimatter had been perfectly balanced, they would have destroyed each other completely, leaving nothing but light, photons streaming through an empty universe. There would be no atoms, no molecules, no stars, no planets, no life. But instead, there was an imbalance. And that imbalance made existence possible. Why? We don't know. There are theories, ideas involving subtle differences in how matter and antimatter behave under certain conditions, violations of symmetries that normally govern particle physics. Experiments at particle accelerators have measured some of these differences, but they're not enough to explain the full asymmetry. Something else must have happened in those first moments, something we haven't yet discovered. After the first few minutes, the universe was filled with a hot plasma of protons, neutrons, electrons, and photons. It was too hot for atoms to form. Anytime a proton and electron tried to combine, a photon would knock them apart. The universe was opaque, foggy with light scattering constantly off free electrons. But as the universe expanded, it cooled. About 380,000 years after the Big Bang, it cooled enough for atoms to form for the first time. Protons and electrons combined into hydrogen and some helium, and the photons that had been scattering around could finally travel freely. This moment is called recombination, and those photons have been traveling through space ever since, stretched and cooled by the expansion, now appearing as the cosmic microwave background, a faint glow of microwave radiation filling the entire sky. This ancient light is the oldest thing we can see. It's a snapshot of the universe as it was 380,000 years after the beginning, nearly uniform in temperature, but with tiny fluctuations, ripples in density that would later grow into galaxies and clusters. By studying this light in exquisite detail, cosmologists can learn about the universe's composition, its age, its geometry, the seeds of structure that grew into everything we see today. The cosmic microwave background is everywhere. It's passing through you right now, a few hundred photons from the edge of the observable universe crossing through your body every second. Ancient messengers from a time long before the Earth, before the sun, before any stars existed at all. You are bathed in this light, constantly, gently, though you cannot see it or feel it. After recombination, The universe entered a period sometimes called the cosmic dark ages. There were no stars yet, no galaxies. Just vast clouds of hydrogen and helium drifting through expanding space, slowly clumping together under gravity's patient pull. For hundreds of millions of years, the universe was dark, lit only by the fading glow of the Big Bang. Then, slowly, the first stars began to form. These were massive stars, much larger than most stars today, burning hot and bright, living fast and dying young in spectacular supernova explosions. Their light pierced the darkness. Their radiation ionized the surrounding hydrogen, stripping electrons from atoms and clearing the cosmic fog. This epoch, called Cosmic Dawn, transformed the universe from a dark, neutral expanse into a transparent, ionized one, opening windows through which light could travel across vast distances. Those first stars also forged the first heavy elements. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. Everything else, every atom of carbon, nitrogen, oxygen, iron, every element in your body, was made later inside stars. Stars fuse lighter elements into heavier ones in their cores, and when massive stars explode, they scatter those elements into space, enriching the gas clouds from which new stars and planets will form. We are made of stardust. This isn't poetic exaggeration. It's literal truth. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in the nuclear furnaces of stars that lived and died billions of years ago, long before the sun or earth existed. You are a collection of atoms with a history stretching back to the early universe, gathered together briefly into the form you call yourself, before eventually returning to the cosmos, recycled again into future stars, future worlds, future possibilities. Let's turn our attention now to the large-scale structure of the universe, the cosmic web that connects everything. If you could step far back, far enough to see billions of light years in every direction, you would see that galaxies are not scattered randomly. They form patterns, immense filaments, and sheets, like the foam in a bubble bath or the threads in a spider's web, with vast empty regions, voids, in between. This structure formed gradually over billions of years as dark matter and ordinary matter clumped together under gravity. In the early universe, tiny density fluctuations, quantum ripples stretched to cosmic size by inflation, became the seeds of this structure. Regions that were slightly denser pulled in more matter, growing denser still, while regions that were slightly less dense expanded into voids. Dark matter led the way. Because it doesn't interact with light or ordinary matter except through gravity, it could clump together earlier, forming gravitational wells that ordinary matter then fell into. Galaxy clusters formed where filaments crossed, where the density was highest. Galaxies themselves formed along the filaments, like beads on a cosmic thread. The voids, those vast empty regions, are not completely empty. They contain some diffuse gas, some dark matter, and occasionally a few lonely galaxies. But compared to the dense clusters and filaments, they are almost barren, stretching across tens of millions of light years with very little matter to disturb the silence. This cosmic web is not static. It's evolving, always evolving, as galaxies move along the filaments, drawn toward clusters, sometimes colliding and merging, sometimes passing by each other in the vast dark. The whole structure is dynamic, flowing like a very slow river, shaped by gravity and the expansion of space, unfolding on timescales of billions of years. You can imagine yourself floating in this web, drifting along a filament, past galaxies glowing softly in the darkness, across voids so empty that the nearest galaxy might be millions of light years away, toward a cluster where thousands of galaxies gather, their combined gravity pulling you gently closer. It's a peaceful journey, one that requires no effort, only patience and time. Our Milky Way galaxy is part of a small group called the Local Group, which includes the Andromeda Galaxy and a few dozen smaller galaxies. The Local Group, in turn, is part of the Virgo supercluster, and the Virgo supercluster is part of an even larger structure called the Laniakea supercluster, a sprawling network of over 100,000 galaxies stretching across 500 million light years, all moving together through space, drawn by a gravitational basin called the Great Attractor. The Great Attractor is not a single object but a region of space, hidden partly behind the plane of the Milky Way, where the density of galaxies is unusually high. Its gravity tugs on our Local Group and countless other galaxies, pulling us slowly toward it at hundreds of kilometers per second. But because space itself is expanding, and because the expansion is accelerating, we will never actually reach it. We are like travelers on a moving walkway that's accelerating backward faster than we can walk forward. We move toward the Great Attractor, but the expansion of space carries us away, and eventually, the distance between us will only grow. This is the fate of the universe under dark energy's influence. As the expansion accelerates, galaxy clusters will become more and more isolated. The filaments connecting them will stretch and thin. Eventually, billions of years from now, galaxies outside our Local Group will be carried so far away by expansion that their light will no longer reach us. The night sky will grow darker, emptier. Future civilizations, if any exist, will look up and see only their own galaxy and a few neighbors, with no hint of the vast cosmic web that once filled the universe. But that future is distant, unimaginably distant on human timescales. For now, the universe is still rich with structure, still full of light and motion, and the slow dance of galaxies. Let's come closer to home now, to our own galaxy, the Milky Way. It's a barred spiral galaxy, about 100,000 light years across, containing perhaps 200 to 400 billion stars. No one knows the exact number. From above, it would look like a pinwheel, with spiral arms curving outward from a central bar-shaped structure. From the side, it's a thin disk with a bulge at the center. Our sun is located in one of the spiral arms, about 26,000 light years from the galactic center, orbiting at a speed of roughly 220 kilometers per second. It takes about 250 million years to complete one orbit, a period sometimes called a galactic year. In the entire history of life on Earth, the Sun has completed fewer than 20 orbits around the galaxy. Dinosaurs roamed the Earth only 1 or 2 galactic years ago. The center of the Milky Way is a crowded, violent place. Stars there are packed much more densely than in our neighborhood, and at the very heart of the galaxy, hidden within a cloud of gas and dust, lies a supermassive black hole called Sagittarius A, with a mass about 4 million times that of the Sun. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. They form when massive stars collapse at the end of their lives. Or, in the case of supermassive black holes like Sagittarius A, through processes we don't yet fully understand, perhaps by the merging of many smaller black holes, or the direct collapse of massive gas clouds in the early universe. Sagittarius A is not currently very active. It's not consuming much matter, so it's relatively quiet, barely glowing compared to the active galactic nuclei found in some other galaxies. But occasionally, a star or gas cloud wanders too close, and we see a brief flare of radiation as material falls toward the event horizon, heated to millions of degrees by friction and compression before vanishing forever. Black holes are strange objects, not just because of their extreme gravity, but because they challenge our understanding of physics in fundamental ways. Near a black hole, space-time is so severely curved that time itself behaves differently. If you watch someone fall toward the event horizon from a safe distance, you would see them slow down, moving more and more sluggishly as they approached, their clock ticking slower and slower, until they seemed to freeze at the horizon, never quite crossing it, but from the perspective of the person falling. Time would feel normal, and they would cross the horizon in finite time, feeling nothing unusual at that moment, before being torn apart by tidal forces deeper inside. This is one of the paradoxes of black holes. What happens to the information carried by objects that fall in? According to quantum mechanics, information cannot be destroyed. But according to general relativity, anything that crosses the event horizon is lost forever, unreachable, as if it had been erased from the universe. This conflict, called the black hole information paradox, is one of the deepest unsolved problems in theoretical physics, hinting that we need a new theory, a theory of quantum gravity, to fully describe what happens at the boundary between the very large and the very small, where Einstein's relativity and quantum mechanics collide. Some physicists think the resolution involves something called Hawking radiation, a quantum effect predicted by Stephen Hawking, in which black holes slowly evaporate over time by emitting particles. The process is excruciatingly slow for large black holes, taking far longer than the current age of the universe. But in principle, a black hole is not entirely black. It glows faintly, and over unimaginable timescales, it shrinks, eventually vanishing in a final burst of radiation. If Hawking radiation carries information out of the black hole in some subtle way, the paradox might be resolved, though the details remain hotly debated. You don't need to solve this paradox tonight. You can let it rest, a quiet question at the edge of human knowledge, a reminder that the universe still holds mysteries even the greatest minds cannot yet unravel. There's something soothing about that, something that connects you to every scientist and thinker who has ever looked up at the sky and wondered. Let's drift outward now, beyond our galaxy, into the space between galaxies. This space is not empty. It's filled with a thin, diffuse gas called the intergalactic medium, mostly hydrogen and helium, left over from the Big Bang, and enriched slightly by elements blown out of galaxies by supernova and stellar winds. The density of this gas is incredibly low, often just 1 atom per cubic meter or even less. But it's not nothing. In some regions, the intergalactic medium is heated to millions of degrees by shocks and radiation from galaxy clusters or active galactic nuclei. This hot gas emits X-rays, faint but detectable by space telescopes. By mapping this X-ray glow, astronomers can trace the distribution of gas across the cosmic web, revealing the invisible threads of dark matter that guide its flow. The intergalactic medium is also shaped by cosmic rays, high-energy particles accelerated to near-light speeds by supernova shocks, black hole jets, and other violent events. These particles stream through intergalactic space, carrying energy far from their sources, ionizing gas, generating magnetic fields, and influencing the formation of new galaxies. Cosmic rays occasionally reach Earth, colliding with atoms in our atmosphere and creating showers of secondary particles that rain down on the surface. Some of these particles pass through you right now, mostly harmless, just another invisible thread connecting you to distant cosmic events. A supernova that exploded thousands of light years away. A black hole jet launched from a galaxy billions of light years distant. Their influence reaches you here, in this room, in this quiet moment. There's a subtle poetry in that, a sense of connection across scales so vast they defy comprehension. You are not separate from the universe. You are part of it, woven into its fabric, breathing its atoms, bathed in its ancient light, touched by its high-energy particles. The boundary between you and the cosmos is not a wall. It's a gradient, a gentle transition from the dense matter of your body to the thin matter of the air, the thinner matter of interplanetary space, the even thinner matter of the intergalactic medium, all of it continuous, all of it one. Now let's turn our attention to the question of why we exist at all, why there is something rather than nothing, and why that something is matter rather than antimatter. This brings us back to the asymmetry we touched on earlier, the tiny imbalance in the early universe that allowed matter to survive. As the universe expanded and cooled, this dance slowed down. Eventually, the temperature dropped below the threshold needed to create new pairs, and the existing particles and antiparticles annihilated each other one last time. If the numbers had been perfectly balanced, that would have been the end. The universe would be filled with light and nothing else, but there was an imbalance. For every billion particle-antiparticle pairs, there was one extra particle, one leftover bit of matter. Those billion pairs annihilated, leaving behind a sea of photons, and the one extra particle survived. That leftover matter is everything we see today. Every star, every planet, every atom in your body, all of it came from that tiny excess. Why was there an excess? What caused the asymmetry? Physicists call this the baryon asymmetry problem. Baryon being the term for particles like protons and neutrons, the building blocks of atomic nuclei. To create an asymmetry, 3 conditions must be met. Conditions first outlined by the Russian physicist Andrei Sakharov. First, there must be processes that violate baryon number, that can create or destroy baryons. Second, there must be violation of charge and parity symmetry, subtle differences in how particles and antiparticles behave. Third, these processes must occur out of thermal equilibrium, in conditions where the universe is changing faster than particles can equilibrate. The early universe provided the third condition automatically. It was expanding and cooling rapidly, far from equilibrium. And experiments have confirmed that charge and parity symmetry are violated, at least slightly, in the weak nuclear force. but the violations observed so far are too small to explain the full asymmetry. Something else must have happened, something we haven't detected yet. One possibility involves grand unified theories, attempts to unify the electromagnetic, weak, and strong nuclear forces into a single framework. In these theories, at extremely high energies, far beyond what we can reach in particle accelerators, new particles and interactions might exist that violate baryon number and produce the asymmetry. Another possibility involves the neutrino, the ghostly, nearly massless particle that barely interacts with anything. If neutrinos and antineutrinos behave differently in certain ways, processes in the early universe involving neutrinos might have generated the excess matter. We don't know which, if any, of these ideas is correct. We may not know for a long time. The energies involved are so high, the process is so rare, that detecting them directly might be impossible. But physicists continue to search, using indirect methods, looking for tiny violations of symmetries in particle decays, searching for rare processes that hint at deeper physics. And even if we never find the full answer, even if the exact mechanism remains hidden, we know the outcome. We know that an asymmetry existed because we exist. The fact that you are here, breathing, thinking, alive, is proof that the universe chose matter over perfect symmetry, existence over oblivion. There's something quietly profound about that. You are not an accident in the sense of being random or meaningless. You are the outcome of a very specific set of conditions, a universe with certain laws, certain constants, certain initial conditions that allowed complexity to emerge, allowed stars to form and planets to coalesce, and life to begin. If the asymmetry had been slightly different, too small or too large, the universe might have been very different, perhaps devoid of galaxies, perhaps too simple to support life. But you don't need to dwell on what might have been. You can simply rest in what is, in the fact of your existence, unlikely and precious. A brief pattern of matter and energy aware of itself, aware of the universe it came from. Let's talk now about the shape of the universe, its geometry, its curvature. This might sound abstract, but it has real consequences, affecting how light travels, how distances change, and what the ultimate fate of the cosmos might be. According to general relativity, mass and energy curve space-time, and that curvature is what we experience as gravity. On small scales, the curvature is local, created by individual objects like stars or black holes. But on the largest scales, the entire universe has a curvature, determined by its total density. There are three possibilities. If the density is high enough, the universe curves back on itself like the surface of a sphere. This is called a closed universe. And in this case, if you traveled in a straight line for long enough, you would eventually return to your starting point, like circumnavigating the Earth. A closed universe has finite volume, though no edge, and it might eventually stop expanding and collapse back on itself in a big crunch. If the density is too low, the universe curves the opposite way, like the surface of a saddle. This is called an open universe, and it extends infinitely in all directions. It will expand forever, faster and faster, until everything is cold and dark and infinitely diluted. But there's a third possibility, a knife edge between the other two. If the density is exactly right, the universe is flat, with no curvature at all, at least on the largest scales. Parallel lines stay parallel. Triangles add up to 180 degrees. A flat universe is also infinite, and it will expand forever, though more slowly than an open universe, gradually coasting toward a cold, dark future. Measurements of the cosmic, microwave background, and other observations suggest that our universe is very, very close to flat. The total density, including matter, and dark energy, appears to balance almost perfectly with the critical density needed for flatness. This is another mystery, another fine-tuning that cosmologists don't fully understand. Why is the universe so flat? Why not slightly open or slightly closed? One answer is cosmic inflation, that brief period of exponential expansion in the first fraction of a second after the Big Bang. Inflation would have stretched any initial curvature to nearly zero, making the observable universe appear flat, even if the whole universe is curved on larger scales we cannot see. It's like inflating a balloon until a small patch of its surface looks nearly flat. This flatness has implications. If the universe is flat and infinite, then everything that can happen will happen infinitely many times, somewhere out there beyond the cosmic horizon. There might be other regions of space, impossibly far away, where galaxies and stars and planets form, where civilizations arise, where someone much like you looks up at their sky and wonders about the universe. This is not science fiction. This is a straightforward consequence of an infinite universe with finite possibilities. If space goes on forever and matter is distributed roughly uniformly on large scales, then every possible configuration of atoms, every possible history, must repeat an infinite number of times across the vastness. But those other use, if they exist, are beyond the cosmic horizon. Their light will never reach you. You will never meet them or communicate with them. They are part of the same universe, the same physical reality, but forever separated by the expansion of space. You can think of them as parallel stories, unfolding in isolation, each one real and complete and utterly independent. Or you can let go of that thought entirely, let it drift away like a dream. It's not something you need to carry. The universe is vast enough without trying to imagine its infinite extent. Let's turn now to the possibility that the universe might not be alone, that there might be a multiverse, an ensemble of universes, each with its own laws, its own constants, its own history. This is a speculative idea, one that pushes at the boundaries of science, but it arises naturally from several different lines of thought, and it offers one possible answer to some of the fine-tuning puzzles we've encountered. Cosmic inflation, for instance, might not have been a one-time event. In many versions of inflationary theory, once inflation starts in one region of space, it never completely stops everywhere. It ends in some regions, creating pocket universes like ours, while continuing in others, generating new pockets endlessly. This is called eternal inflation, and it suggests that our universe is just one bubble in an infinite froth of universes, each one a separate space-time, each one potentially with different physical properties. In some of these universes, the fundamental constants might be different. The strength of gravity, the mass of the electron, the cosmological constant, all of these could vary from universe to universe. Most universes might be inhospitable, too chaotic or too simple to support complexity, but a few, like ours, might have the right conditions for stars and planets and life. This idea is sometimes called the anthropic principle. We find ourselves in a universe with life-friendly properties, not because the universe was designed for us, but because only in such universes can observers exist to ask the question. It's a selection effect. We observe a universe capable of producing us, because we couldn't exist in any other kind. Some scientists find this explanation unsatisfying. It doesn't predict anything specific, doesn't tell us why the constants have the values they do, only that they must lie within a certain range for us to be here. But others argue that if the multiverse is real, and if the constants vary, then the anthropic principle is simply a fact we must accept, a constraint on what we can observe. There's no way to know for sure, not yet. The other universes, if they exist, are causally disconnected from ours. We cannot see them, cannot visit them, cannot directly test their existence. But there might be indirect evidence. If bubble universes collided in the distant past, they might have left imprints on the cosmic microwave background, subtle patterns that could, in principle, be detected. So far, no such patterns have been confirmed, but the search continues. Another source of multiverse thinking comes from quantum mechanics. In the standard interpretation, when a quantum system is measured, its wave function collapses, and one of many possible outcomes becomes real. But in an alternative interpretation, called the many worlds interpretation, the wave function never collapses. Instead, every possible outcome occurs, each in a different branch of reality, a different universe within the multiverse. In this view, every time a quantum event occurs, the universe splits. Every decision, every random decay, every coin flip creates new branches, new worlds, all equally real, all existing in parallel. You are not one person in one universe, but an unfathomably large collection of versions of yourself, spread across countless branches, each one experiencing a slightly different history. This interpretation is mathematically elegant and avoids some of the conceptual difficulties of wave function collapse, but it comes at a cost. It requires believing in an enormous, perhaps infinite, number of unobservable universes. Many physicists find this too extravagant, preferring interpretations that don't multiply worlds unnecessarily. But the many worlds interpretation is still a legitimate possibility, and it's studied seriously by researchers trying to understand the foundations of quantum mechanics. Whether the multiverse is real or not, whether it arises from inflation or quantum mechanics or some other mechanism, the idea invites a certain kind of humility. It suggests that our universe, vast as it is, might be just a tiny part of a much larger reality, one that we can only glimpse through mathematics and indirect reasoning. And yet, this doesn't diminish the significance of our own universe, our own existence. Even if there are countless other worlds, this one is yours. This is where you live, where you breathe, where you experience the world. That makes it special, not in an absolute sense, but in a personal one. It's the only universe you will ever know, the only one you can touch and explore and love. Let's come back down to Earth now, to the solar system, to the pale blue dot that's home. The Earth is about 4.5 billion years old, formed from the disk of gas and dust that surrounded the young sun. In the beginning, it was a molten ball, bombarded by asteroids and comets, too hot and chaotic for life. But gradually, it cooled. Water vapor condensed into oceans. An atmosphere formed, mostly carbon dioxide and nitrogen at first, later transformed by life into the oxygen-rich air we breathe today. Life arose early, remarkably early, perhaps as soon as the planet was cool enough to allow liquid water. The first life forms were simple, single-celled organisms, bacteria and archaea, living in the oceans, feeding on chemicals dissolved in the water. For billions of years, life remained simple, invisible to the naked eye, but it was changing the planet, releasing oxygen as a waste product of photosynthesis, altering the chemistry of the atmosphere and oceans. About 600 million years ago, complex multicellular life appeared, plants and animals, diversifying rapidly in what's called the Cambrian explosion. Life colonized the land. Forests grew. Dinosaurs roamed for 165 million years, far longer than humans have existed, before being wiped out by an asteroid impact 66 million years ago. Humans, Homo sapiens, have been around for only about 300,000 years. A blink of an eye in cosmic time. Civilization, the building of cities and writing and agriculture, is even younger, only about 10,000 years old. All of recorded history, everything you've ever read in a history book, fits into the last few thousand years, a tiny sliver of the Earth's story, and an infinitesimal fraction of the universe's. And yet, in that brief time, humans have done something remarkable. We've looked up. We've asked questions. We've built telescopes and spacecraft. We figured out how old the universe is, how it began, how it's structured. We've discovered that we're made of stardust, that the atoms in our bodies were forged in ancient stars. We've learned to read the light from galaxies billions of light years away, to hear the faint echoes of the Big Bang, to see the invisible through mathematics and careful reasoning. This is an extraordinary achievement, one worth pausing to appreciate. You are part of a species that has, in a very real sense, woken up to the cosmos, become aware of its place within the vast unfolding of space and time. That awareness is precious. It's a gift, a responsibility, a source of wonder, but it's also humbling. The more we learn, the more we realize how much we don't know. Dark matter, dark energy, the origin of the baryon asymmetry, the nature of black holes, the possibility of a multiverse, all of these are open questions, puzzles waiting to be solved, and there are almost certainly other mysteries we haven't even thought to ask about yet, phenomena beyond our current understanding, waiting quietly for future generations to discover. Science is not a finished project. It's an ongoing process, a conversation between humanity and the universe, each generation adding to the knowledge, refining the theories, asking new questions. You are part of that conversation, even if you never publish a paper or build a telescope. Every time you look up at the night sky and feel a sense of wonder, every time you ask why or how, you are participating in the human quest to understand. And you don't need to understand everything. You don't need to hold all the details in your mind. You can let most of it drift away, keeping only the feeling, the sense of awe and connection, the quiet joy of knowing that the universe is larger and stranger and more beautiful than you can fully grasp. Let's think now about the future. The distant future, billions of years from now. when the universe will be very different from what it is today. The sun, our sun, has about 5 billion years of life left before it exhausts the hydrogen in its core and begins to swell into a red giant, growing so large that it will engulf Mercury and Venus, and possibly the Earth. But long before that, in about 1 billion years, the sun will brighten enough to boil away Earth's oceans, making the planet uninhabitable for life as we know it. If humanity survives that long, we will need to leave to find new homes around other stars, or in space habitats, or perhaps in ways we cannot yet imagine. But even if we don't, even if humanity is long gone by then, life might continue elsewhere, on other worlds, in other forms, carrying the torch of awareness into the deep future. Stars like the sun will continue to form for trillions of years, though at a steadily declining rate as the supply of gas is used up. Eventually, star formation will stop. The last stars will burn out, and the galaxies will go dark, filled with the corpses of stars, white dwarfs, neutron stars, black holes, and planets drifting through the void on even longer timescales. The galaxies themselves will change. Stars will be ejected from galaxies through gravitational interactions, or they will spiral into the central black holes. The galaxies will evaporate, dispersing their stars into the emptiness, leaving only the black holes behind. And the black holes, even the supermassive ones, will eventually evaporate through Hawking radiation, a process so slow that it takes 10 to the power of 100 years or more. A 1 followed by 100 zeros, a number so large that it's hard to conceive. But eventually, given enough time, even the black holes will vanish, leaving the universe cold and empty and dark, a thin soup of particles and radiation at a temperature barely above absolute zero. This is sometimes called the heat death of the universe, the state of maximum entropy, where no energy is available to do work, where nothing changes, where time, in a sense, loses its meaning because there are no processes left to mark its passage. It sounds bleak, perhaps, but it's so far in the future that it's almost abstract, more of a thought experiment than a real concern. The timescales involved are so vast that the entire history of the universe so far, 13.8 billion years, is nothing. A brief spark at the very beginning. And who knows? Perhaps something will happen that we haven't predicted. Perhaps the laws of physics allow for processes we haven't discovered, ways for complexity to re-emerge even in the deep cold of the far future. Or perhaps the multiverse is real, and new universes are constantly being born, each one a fresh beginning, a new chance for stars and galaxies and life to arise. The point is not to worry about the distant future. The point is to appreciate the present, the fact that right now, the universe is alive with light and motion and complexity, that you are here to witness it, to think about it, to feel a sense of connection to it. Let's drift now into quieter thoughts, softer reflections. Think about the night sky as it appears from a dark place, far from city lights. If you've ever seen it, truly seen it, you know how dense the stars can be, how the Milky Way stretches across the sky like a river of light. Each of those stars is a sun, some smaller than ours, some larger, some with planets, some alone. And between the stars, vast distances, light years of empty space, crossed only by occasional atoms and photons, and beyond the Milky Way, beyond the faint glow of our galaxy, lie other galaxies, invisible to the naked eye, but present nonetheless. Billions of them, each one a city of stars, each one with its own history, its own structure, its own place in the cosmic web. You are connected to all of it, not just metaphorically, but physically. The atoms in your body have been on a long journey, forged in stars, scattered by supernovae, drifting through interstellar space, gathering into the cloud that formed the sun and earth, cycling through rocks and oceans and atmosphere, through plants and animals, and finally, briefly, assembled into you. When you breathe, you're inhaling atoms that were once part of dinosaurs, of ancient forests, of the first bacteria that learned to photosynthesize. When you look at the stars, the photons entering your eyes have traveled for years, decades, centuries, depending on how far the star is, crossing the emptiness just to end their journey in your retina. There's a deep intimacy in that, a sense that you are not separate from the universe, not a stranger or an intruder, but a part of it, as natural as a star or a galaxy, as much a product of the same laws and the same history. And yet, you are also unique. The particular arrangement of atoms that makes you, the memories and thoughts and feelings that constitute your awareness, have never existed before and will never exist again. You are a once-only event, a singular expression of the universe's creativity that's worth honoring, worth appreciating, not with grand gestures or dramatic declarations, but quietly, gently, in moments like this, when you're lying in the dark, drifting towards sleep, simply being. You can let go of the need to understand everything. You can let go of the desire to know all the answers. The universe will keep its secrets, at least for now, and that's okay. That's part of the beauty, the fact that there's always more to discover, always new questions to ask, always a sense of wonder waiting just beyond the edge of knowledge. And in the meantime, you can rest. You can let your body relax, let your breathing slow, let your thoughts grow soft and blurry, like starlight fading into the glow of dawn. The universe is still there, still vast, still mysterious, but you don't need to hold it in your mind right now. You can let it be, let it continue its slow unfolding, while you drift into sleep, into dreams, into the gentle darkness that holds you safe. As you settle deeper into rest, let's take one more gentle journey, this time focusing on the smallest scales, the quantum realm where particles flicker in and out of existence, where certainty dissolves into probability, where the rules that govern the everyday world break down, and something stranger emerges. Quantum mechanics is the physics of the very small, of atoms and electrons and photons, and it describes a world that feels fundamentally alien to our everyday experience. In the quantum realm, particles don't have definite positions or velocities until they're measured. They exist in a state of superposition, occupying many possibilities at once, like a coin that's both heads and tails until you look at it. When you measure a quantum system, you collapse its wave function, forcing it to choose one outcome from many. But before measurement, all outcomes exist simultaneously, at least mathematically. An electron can be in two places at once. A photon can travel through two slits at the same time, interfering with itself as if it were a wave, even though we detect it as a particle. This is not just a philosophical puzzle. It's a real feature of nature, confirmed by countless experiments. Quantum mechanics is the most successful physical theory ever developed, making predictions with extraordinary precision, enabling technologies like transistors and lasers and MRI machines. And yet, no one fully understands what it means, what it's telling us about the nature of reality. There are many interpretations, many ways to think about what's happening when a wave function collapses, but none of them feel completely satisfying. Some interpretations say that the wave function represents our knowledge, not reality itself, and measurement simply updates our information. Others say that the wave function is real, and measurement creates reality, calling it into being from a haze of possibilities. Still others, like the many worlds interpretation, say that all possibilities are real, each one unfolding in a separate universe. Physicists argue about which interpretation is correct, or whether the question even makes sense. But regardless of interpretation, the predictions are the same, the experiments give the same results, and the world continues to be quantum, strange and beautiful, and utterly indifferent to our confusion. There's something peaceful about accepting that strangeness, about acknowledging that the universe doesn't have to make sense in familiar terms, that it's allowed to be weird. You don't need to understand quantum mechanics to appreciate it. You don't need to visualize superposition or wrap your mind around wave-particle duality. You can simply know that the world is richer and more subtle than it appears, that beneath the surface of ordinary experience lies a realm of possibility and indeterminacy, where the future is not yet written, where reality is, in a sense, still unfolding. This quantum indeterminacy has implications even on cosmic scales. In the early universe, during the period of inflation, quantum fluctuations, tiny random variations in the energy of the vacuum were stretched to enormous sizes, becoming the seeds of galaxies and large-scale structure. The pattern of galaxies across the sky, the distribution of matter and voids, all of it traces back to quantum randomness amplified to cosmic proportions. So in a very real sense, the universe's structure is quantum. The reason galaxies are where they are, the reason the Milky Way exists in this particular location, all of it is ultimately due to random quantum events that occurred in the first fraction of a second after the Big Bang. If you could rewind the universe and play it again, those quantum events might turn out differently, and the pattern of galaxies would be different too. We might not exist, or we might exist somewhere else, in a different galaxy, under a different sky. But this is the universe we have, the one that unfolded from this particular set of quantum fluctuations, and it's the only one we'll ever know. And that's enough. It's more than enough. It's everything. Let's think about light one more time, about the photons that have traveled from distant galaxies to reach you, carrying information across space and time. When you look at a star, you're not seeing it as it is now. You're seeing it as it was when the light left, years or decades or centuries ago, depending on the star's distance. The star might have changed since then. It might have died, exploded, leaving behind a neutron star or a black hole. But the light continues traveling, a messenger from the past, and when it reaches your eye, it delivers its message, a moment frozen in time. For very distant galaxies, this time delay is billions of years. When astronomers observe galaxies at the edge of the observable universe, they're seeing those galaxies as they were shortly after the Big Bang, young and small and vigorously forming stars. Those galaxies are not there anymore, not in that form. They've evolved, merged with others, grown old, but their ancient light is still traveling, and it's reaching us now, allowing us to witness the early universe directly. In a sense, looking out into space is looking back in time. The farther you look, the farther back you see, and the cosmic microwave background, the oldest light of all, shows us the universe as it was 380,000 years after the Big Bang, the moment it became transparent for the first time. This means that the universe has a kind of memory, encoded in light. Everything that has ever happened, everywhere in the cosmos, is still out there, its light traveling through space, carrying the information forward. If you could catch up to a photon that left Earth 1,000 years ago, you could, in principle, see what the Earth looked like then. The light from every moment in history is still traveling, spreading outward at the speed of light, a permanent record written in photons. Of course, you can't catch up to that light. It's moving away from you at the speed of light, and nothing can go faster. But the idea is beautiful nonetheless. The idea that the past is not gone, not erased, but preserved in the structure of space-time, in the light that continues its journey through the cosmos. This light connects everything. A photon emitted by a star in a distant galaxy billions of years ago travels through the expanding universe, through intergalactic space, through the Milky Way, through Earth's atmosphere, and into your eye, ending a journey that began before the Earth existed. In that moment, you are connected to that distant star, to the processes that created the photon, to the history of the universe that allowed it to reach you. And you are made of light too, in a way. The energy that powers your body comes from the sun, from photons that traveled 93 million miles in about 8 minutes, were absorbed by plants through photosynthesis, and were passed along the food chain until they reached you. Every movement you make, every thought you think, is powered ultimately by sunlight, by the fusion reactions in the sun's core that create photons, by the long journey those photons take from the core to the surface, and then across space to Earth. You are a pattern of matter animated by light, sustained by the energy of a star, aware, for a brief time, of your place in the cosmos. When your life ends, that pattern will dissolve, the atoms will return to the environment, to be recycled into new forms, new possibilities. But the awareness you have now, the thoughts and feelings and experiences, these are unique, unrepeatable, precious. So rest in that preciousness. Let yourself be held by the universe, by the dark matter that fills the space around you, by the photons streaming through the room, by the atoms in your body that were once part of stars. You belong here. You are not a mistake or an accident. You are a natural expression of the universe's tendency toward life, toward awareness. And now, let all the details go. Let the names and numbers drift away. Let the concepts blur and soften. You don't need to hold on to any of it. The universe will remember. It will keep spinning, expanding, evolving, with or without your attention. Your job now is simply to rest, to let go, to allow sleep to come. Think of yourself floating in space, not in a frightening way, but gently, peacefully, surrounded by stars. There's no cold, no vacuum, just the soft glow of distant galaxies. The quiet presence of the cosmic web, the ancient light of the Big Bang washing over you like a warm blanket. You are safe here. You are home. The universe is vast, yes, but it's also intimate, woven through with connections, with light and matter and energy, flowing in patterns too complex to fully comprehend, but beautiful nonetheless. As you drift toward sleep, you can imagine those patterns, the slow dance of galaxies, the formation of stars from clouds of gas, the forging of heavy elements in supernova explosions, the scattering of those elements into space, the gathering of new clouds, new stars, new planets, the emergence of life, of awareness, of you. It's a cycle that has repeated countless times, across billions of years, in countless places, and it will continue long after you're gone. The universe constantly renewing itself, creating new forms, new possibilities, new moments of beauty and wonder. But this moment, this particular arrangement of atoms and awareness, this is yours, and it's enough. You don't need anything more. You don't need to understand everything or accomplish everything or experience everything. You just need to be here now, gently letting go, allowing the mystery to remain mysterious, allowing the universe to be vast and unknowable and beautiful. Let your breathing slow. Let your muscles relax. Let your thoughts grow quieter, softer, like stars fading in the morning sky. There's nothing you need to do, nothing you need to solve. The questions will still be there tomorrow and the day after, waiting patiently for anyone who wants to explore them. But tonight, you can rest. You can let the universe hold you, the way it holds every particle, every photon, every galaxy. You can trust that the cosmos will continue its slow, majestic unfolding, and that you, for this brief moment, are part of that unfolding, a note in the symphony, a brushstroke in the painting, a thought in the mind of the universe thinking about itself. And now, as you sink deeper into rest, deeper into the quiet darkness of sleep, let yourself dissolve a little. Let the boundaries between you and the universe soften. You are made of stardust, and stardust doesn't end. It transforms, it changes form, but it persists. Part of the ongoing story of matter and energy dancing through space-time. One day, the atoms in your body will be part of something else, somewhere else, perhaps a cloud of gas, perhaps a planet orbiting a sun that hasn't been born yet. And in that sense, you will continue, not as yourself, but as matter, as possibility, as part of the universe's endless creativity. But for now, for this moment, you are here, you are you, and that's a gift. So rest in that gift. Let yourself be cradled by the darkness, by the silence, by the gentle presence of the cosmos all around you. There's nothing more you need to know tonight. The universe has shared some of its secrets with you, and you've listened, and that's enough. Now you can let go. Let sleep come. Let dreams carry you wherever they will, knowing that when you wake, the universe will still be here, still vast, still mysterious, still beautiful, waiting for you to look up and wonder once again. And now, as you sink deeper into rest, deeper into the quiet darkness of sleep, let yourself dissolve a little. Let the boundaries between you and the universe soften. You are made of stardust, and stardust doesn't end. It transforms, it changes form, but it persists. Part of the ongoing story of matter and energy dancing through space-time. One day, the atoms in your body will be part of something else, somewhere else. Perhaps a cloud of gas, perhaps a planet orbiting a sun that hasn't been born yet. And in that sense, you will continue, not as yourself, but as matter, as possibility, as part of the universe's endless creativity. But for now, for this moment, you are here, you are you, and that's a gift. So rest in that gift. Let yourself be cradled by the darkness, by the silence, by the gentle presence of the cosmos all around you. There's nothing more you need to know tonight. The universe has shared some of its secrets with you, and you've listened, and that's enough. Now you can let go, let sleep come, let dreams carry you wherever they will, knowing that when you wake, the universe will still be here, still beautiful, waiting for you to look up and wonder once again. Sleep well. Rest deeply. The stars are watched over this planet for billions of years, the way they'll continue to watch long after you're gone. You are held by the same forces that hold galaxies together, guided by the same laws that govern the dance of particles and the expansion of space. And in this moment, that's all you need to know. You are part of the universe, and the universe is part of you. And there's nowhere else you need to be, nothing else you need to become. Just this, just rest, just the gentle fading of thought into sleep, into dreams, into the quiet peace of the night. Good night.